Good morning. In the last session I have been talking about the role of alloying elements on segregation and its consequences. I have mentioned that phosphorus and sulfur, these are the two elements which we have to look into very carefully because their role is deleterious. Why it is deleterious? I had mentioned that small k, the value of partition coefficient between solid and liquid, which is less than 1 for all alloying elements, but for phosphorus and sulfur they are very low. Like I have mentioned, phosphorus in delta solidification it is 0.23, sulfur is 0.05. You see, these are very low compared to manganese and silicon. Manganese silicon is 0.76, 0.77. So compared to normal alloying elements like manganese silicon, this table is just to give a relative relative values of small k for the different alloying elements. So what we find here is that phosphorus and sulfur are very deleterious because their values, small k values, partition coefficient values are quite low, and between delta and gamma, if the solidification is through delta or through gamma, depending on that, the values for small k with respect to gamma, that means austenitic solidification, are still lower compared to delta ferrite. 0.23 in delta ferrite for phosphorus, 0.13 for gamma. For sulfur it is 0.05, for delta ferrite it is 0.035, the value of k, it is quite small, quite low for austenitic solidification. So what is the impact of this? Impact is this high microsegregation of phosphorus and sulfur, they lower the actual solidus temperature compared to the equilibrium solidus. This I have been telling repeatedly that not only there is segregation, but the impact of segregation is the actual solidus is lowered compared to the equilibrium solidus. So if the actual solidus is lowered, the solidification range, the temperature difference between the liquidus and the actual solidus also increases. If this is low, liquidus is not much affected. So the difference between TL and TSA, that means the difference between the liquidus and the solidus, is becoming large. So what is the consequence of that? Consequence of that is the, as I have told you earlier, the mushy zone, which is a zone of liquid plus solid, that becomes quite wide, and the actual thickness of solid shell during solidification is relatively narrow. So what is the impact of microsegregation, heavy microsegregation, high microsegregation due to phosphorus and sulfur? Is that the actual solidus is coming down from equilibrium solidus. Consequently, the temperature interval for solidification, the temperature interval between liquidus and actual solidus also is increasing. If TSA comes down, means TL, liquidus remaining more or less similar, the temperature interval for solidification temperature region or zone also increases, and if this increases, the mushy zone will be wider and the actual solid shell during solidification will be narrow. So this has lot of implication on the solidifying strand, its strength, its toughness, everything will depend on that. Now I have also mentioned that fortunately for silicon, for the deleterious effect of silicon, there is a savior, like which we know as manganese. So manganese reacts with sulfur and forms manganese sulfide. So the deleterious effect of sulfur is taken care of to certain extent, because if manganese would not have been there, then sulfur would have reacted with iron, forming iron sulfide, and the melting point of iron sulfide is quite low. So it causes lower TSA. Because of that, effect of sulfur is quite perceptible when it is present as such, when manganese is not there. If manganese by sulfur ratio is high, like is more than 25, then this deleterious effect of sulfur is taken care of to some extent. So that is why we should always use manganese by sulfur ratio of more than 25 to take care of the harmful effect of sulfur. But unfortunately, unlike sulfur, there is no alloying element which is used in steel which can take care of the deleterious effect of phosphorus. So, phosphorus, as I have mentioned here, the small k value is quite low, 0.23 for delta, 0.13 for gamma. That means for gamma solidification, that means when the carbon or carbon equivalent is relatively high, the solidification will be through austenitic mode. In that case, the segregation effect is relatively more compared to segregation happening when the solidification takes place through delta ferrite. So, in case of austenitic solidification, effect of phosphorus and sulfur is more deleterious, and since sulfur effect is taken care of partly by having manganese in steel, so we have to be careful about phosphorus because there is no other alloying element which can take care of the deleterious effect of phosphorus. So, low phosphorus is essential particularly for situation of austenitic solidification, that means for carbon or carbon equivalent more, so more than 0.25, 0.3, 0.4, 0.5. So, these are the chemistries of or the steel compositions which will have more amount of microsegregation because of phosphorus. So, I have also mentioned the some values have been shown here, some calculated values are shown here for a particular level of phosphorus as 0.4. So, if 0.4% phosphorus is present in steel, then how this amount of phosphorus affects the actual solidus and the effective shell thickness, how is it reduced, is shown in this figure. As the carbon content increases, as I have told you, the liquidus temperature there is some decrease. You can get this from the normal phase diagram. So, this is the equilibrium solidus and this is the liquidus. Now, what is the role of 0.4% phosphorus? I have mentioned here that this is at a depth of 25 millimeter from the meniscus. So, if the casting speed is 1.5 meter per minute, then at this depth, that means corresponding to a solidification time of 1 second, this can be found out from this relationship. What is the shell thickness at a time interval of 1 second? So, this value, this means k value, that means solidification constant is 2 millimeter per second to the power 0.5. So, this 2 millimeter is the theoretical shell thickness, this is the 2 millimeter SM, the theoretical shell thickness. But what is the actual shell thickness? That is very important to understand. So, that is why if you calculate what is the effect of segregation of 0.4% phosphorus, then we can calculate what is the CL, that means the final concentration of phosphorus in the last liquid which is to solidify. From the modified shell equation we can find out that, and from there we can find out what was the final final concentration of phosphorus in the last liquid to solidify. From there we can find out what is the actual solidus temperature. So, if we know the actual solidus temperature, then we can know what is the temperature interval. Now, look at these figures. At 0.1% carbon, you see the effect of segregation is relatively less, is minimum. Why it is so? Because the actual segregation is less, because the solidification is taking place through delta ferrite, and only towards the end of solidifications is delta ferrite to austenite transformation is taking place. So, at 0.1% carbon, that means at the start of the peritectic temperature zone, peritectic temperature chemistry, at the start of that, at 0.1% carbon or carbon equivalent, the extent of microsegregation is less. Because of that, the actual solidus also is depressed relatively less. So, the temperature interval for solidification is also relatively less compared to a situation like say at 0.3% carbon, when the level of segregation is more. Because of that, actual solidus is suppressed to a large extent, and because of that the temperature interval for solidification, the difference between TL and TSA, this is quite wide, quite large. Because of this, as I have mentioned, the solid shell is decreasing in thickness and the mushy zone is increasing in thickness. So what is important is to understand here that the solidus temperature, actual solidus temperature is getting decreased due to segregation of phosphorus, and the effect depends on the extent of this effect. Microsegregation depends on what is the carbon or carbon equivalent in the particular steel grade. If you have a 0.1% carbon, that means when we have just at the beginning of the peritectic zone, if the chemistry is 0.1, if the carbon content is 0.1, microsegregation is relatively less and the actual solidus is therefore relatively less depressed, and the difference between liquidus and the actual solidus is relatively less. So the shell thickness is also relatively quite more, solid shell thickness. If the solid shell thickness is more, the mushy zone is relatively narrow. But you look at 0.3% carbon for the same amount of 0.04% phosphorus. Here what is happening is, because of austenitic solidification becoming more and more predominant as you are increasing the carbon content, so segregation is also more. If the segregation is more, the actual solidus is also suppressed to a large extent, and because of that the temperature interval for solidification is more, and consequence of this is the shell thickness is quite narrow. Actual shell thickness, solid shell thickness is narrow, and the mushy zone depth, that means the thickness of the mushy zone is quite wide. So what is happening is, with increasing carbon, mushy zone is becoming wide and the actual solid shell thickness is becoming narrow. This has lot of implication on the strength of the solidifying strand, because the strand consists of what? Strand consists of solid shell, mushy zone and liquid. So if the mushy zone is more wide during solidification, your actual solid shell is narrow, so the strength of the strand also will be less. This we have to keep in mind. This is what I was discussing about the thing, about the relative thicknesses of the solid shell and the mushy zone. The thicknesses depends on basically the temperature intervals. The temperature interval between the liquidus and the actual solidus, the solidification temperature range, is proportional to the mushy zone depth. So if TSA, that means the actual solidus, decreases due to microsegregation, then this temperature interval increases, because TL is more or less constant, it does not vary with microsegregation, but actual solidus is varying. That is what is important to remember. So that means if TSA is decreasing, my actual solidus is decreasing, temperature interval of solidification is increasing, so the mushy zone depth is also relatively more in this case. And if TSA is decreasing, means the temperature interval between TSA and the surface temperature of the solid shell, this is more or less constant. This is the rate of cooling, secondary cooling. So this temperature TSA decreasing means this difference is also less. Here TSA decreasing means this difference is more. Here TSA less means this difference is less. So difference is less means the solid shell is becoming more narrow, the thickness is much less. So what is happening is, this solid shell, this thickness SA is becoming less. SA is becoming less because TSA is decreasing. As TSA decreases, SA also will decrease. So the solid shell actual thickness will be less, and consequently the mushy zone, TSA decreasing means TL minus TSA, this interval is increasing, solidification temperature zone is increasing, the mushy zone is increasing in depth. SS coming in down means the thickness of this, that means SL minus SA is increasing. Therefore, the mushy zone is increasing in thickness. Now I have told that what is the implication of this. The implication is the strength of the solidifying shell. If it's less, means the whole solidifying, solidifying area, that means the whole area of the strand, solidifying strand. During continuous casting, the strand is continuously under movement. So if the strand has less strength, less toughness, it has a lot of problem. There is a chance of crack formation. So this is important to remember. So let me try to mention here the solidifying shell, whatever shell is forming through solidification during casting, undergoes a lot of strain during and after solidification. Unlike continuous casting, here the relatively more of strain will be there, because it is continuously under movement, it is not static. So what are the different strains on the solid shell? First and foremost is the ferrostatic force from the liquid during solidification. When solidification is underway, there is liquid in the strand. So this liquid will create ferrostatic pressure on the solid shell. This shell will be pushed towards the mold when the strand is inside the mold. So this ferrostatic force from liquid steel during solidification is one important reason for generating strain and force on the solid shell. Next is the shrinkage due to solidification. Whenever there is solidification, from liquid solid is forming, whether it is delta or gamma, there will be shrinkage. The extent of shrinkage is less for delta or gamma, whatever it is different for delta or gamma, nevertheless there will be shrinkage. So shrinkage due to solidification is one aspect which will generate some strain and force on the solid shell. Now I have mentioned this delta to gamma, there is a possibility of transformation for certain chemistry. Whenever initially delta is forming, this delta is finally transforming to gamma at low temperature. Now when this delta to gamma transformation takes place, whether during solidification or it may be below solidification, means lower temperature than Solidus, or there may not be delta to gamma transformation at all, because if there is a gamma transformation, gamma solidification, so there is no delta formation. That means for carbon content or carbon equivalent more than 0.5, there will be no delta ferrite formation during solidification. So therefore there is initially austenite and finally solidification takes place entirely through austenite, so there is only austenite. So there is no delta to gamma transformation. So but for certain grades of chemistry, certain grades having chemistry where the carbon is less than 0.5, if carbon is less than 0.1, total solidification will take place through delta, and delta to gamma takes place, transformation takes place at lower temperature, that means lower than the Solidus temperature. So after solidification there is transformation, nevertheless there is transformation. So this delta to gamma transformation will also create a shrinkage and therefore a strain, because the density of delta and gamma are different. So delta to gamma transformation also creates some shrinkage and strain. Now I have mentioned that there may be mechanical strain due to bending and unbending of strand. I think this I had mentioned earlier. Let me just go back to there. Yeah, this is the carved mold caster. That means the mold itself is carved. This mold, this is the mold. Here the mold is indicated as a vertical mold. So the strand which is coming out from the mold is also vertical, like here is a straight mold caster, like this vertical mold caster. So the strand which is coming out of it is vertical. Finally this has to be made horizontal, then only it is possible to cut the solid strand, to get the different cast product of different length. So first it has to be bent, and then after some time it has to be straightened or unbent. That means the strand of a straight mold caster, vertical mold caster, initially it has to be bent and then it has to be made straightened. That means there has to be a straightener. So during bending, what is happening? You look at here. This is the inner radius. This portion is called inner radius. Yeah, this is the inner radius of the caster. The shell, solid shell which has formed near the inner radius, this is subjected to some kind of stress. This is the direction of the stress. Okay. So and the solid shell which is present at the outer radius, it is just the reverse. It is here, some direction of the stress is here this way, and the outer shell it is something just the reverse. Now what is happening during straightening? Straightening, this portion of the shell, the inner shell, it is something, it is just the reverse. So what I am trying to tell you is that during bending and straightening, the solid shell, if it is at the inner radius, it is undergoing certain strain. If it is the outer radius, it is undergoing some strain of other direction. That means of different direction. So both during bending and straightening, there is strain on the solid shell. But if you have a curved mold, that means the mold itself is curved, so the strand is coming out in a curved fashion. So it is not necessary to bend it any longer. What is necessary after some time is to straighten it, so that it is made horizontal. So in case of a curved mold, we have a only straightener, only straightening of the strand is necessary. But in case of a straight mold, we initially must have bending and then straightening. So this is what is important to understand. So here you just look at here. Here it is a compressive force. Look at the direction of the arrows. Here it is a tensile force here. During straightening, just the reverse is happening. At the internal shell, at the internal radius, it is becoming tensile, and at the outer radius it is becoming compressive. Straightening, for curved mold only straightening, no bending is there. So the solid shell at the inner radius is tensile, undergoing tensile strain, and solid shell at the outer radius is undergoing compressive stress or strain. So this is important to remember, like the shell, solid shell is undergoing different type of strain. You see here, this is the internal pressure. You have liquid here within the strand. So this liquid is creating internal pressure. This is called ferrostatic pressure. So this pressure is always coming to the solid shell which is forming. So this is the first source of pressure or tension on a solid shell, or the force on a solid shell is a ferrostatic pressure. Then we have at the bender, we have internal stress at the surface area of the shell. At maximum of the surface, inner and outer, and as you go inside, it is slightly going down. So at the straightener also, there is again a mechanical strain. Here also mechanical. So here it is the directions indicates whether it is compressive or tensile. So what is important to remember, the solid shell is continuously under different strains from different sources. Ferrostatic force is one, then the mechanical strain from bender or the straightener, another source, another is due to solidification, there is a strain, then delta to gamma, there will be a strain. So there are different possibilities of strain at different locations. So we have to understand that what are the sources of strain, at what temperatures these are actually happening, what are the implications of that, what are the causes or the consequences of that. So we have to remember all these aspects to finally arrive at what is their impact on the quality of the cast. That is very important. So while discussing the quality of the cast, that is why we have come to the role of chemistry, the role of segregation, because the role of segregation finally impacts on the shell thickness, solid shell thickness. So that is important. Now, as I was discussing the different strains, I mentioned ferrostatic force from the liquid during solidification. After solidification there is no ferrostatic force, so it is during solidification only this happens. Then shrinkage due to solidification, this also happens during solidification. Then shrinkage due to transformation from delta to gamma, it can happen during solidification or even after solidification, or it may not happen at all for certain chemistries when there is no delta formation. Then I have mentioned mechanical strain due to bending and unbending of strand. Unbending means straightening of strand. I have shown you the examples, whether it will be tensile or it will be compressive. It depends on whether it is the inner radius or the outer radius, whether it is bending or it is straightening, unbending. Again, after solidification is complete, or even before that, when the strand is coming out of the mold, just it has come out of the mold, then what is happening? There is secondary cooling. So secondary cooling means cooling by water on the surface of the strand or by mist cooling. So because of that there is a thermal strain because of temperature difference, because the water or the what is that called, air mist, that means the combination of air and water, that is called mist. This mist is impacting on the surface. Though the surface has maximum cooling, the inside is relatively hot, so there is a thermal strain because of this temperature difference. So the solid shell is also undergoing thermal strain because of this temperature differential. So these are the different strains which are impacting on the solid shell. So the shell must withstand these strains, then only the quality will be okay. If it cannot withstand, then there will be a formation of crack, and if there is a formation of crack, then in the final solidification product also you might be having crack at different depth, at maybe at the surface, maybe subsurface, maybe internal. So these are the problems of quality, these are the issues of quality we have to keep in mind. So that is why strength and toughness of solid shell is very important. So solid shell, whether it is delta or gamma, when the solidification is through delta, you have delta, finally it will transform to gamma. So the during solidification, whether it is delta or gamma, must have adequate strength and toughness at high temperature to withstand the different strains, as I have mentioned you. After certain temperature, that means after solidification, for all types of chemistry of steel it is austenite only, but before that at relatively high temperature you may have delta ferrite depending on certain chemistry. So whether the solid shell is delta or gamma, they must have adequate strength and toughness at high temperature to withstand the different strengths. By high temperature I mean this temperature range 1400 to 600 degrees centigrade. Why this is important? Because solidification is starting maybe at temperature of slightly above 1400 degrees centigrade, but solidification is complete maybe around 1400 for very low carbon grades, but at higher carbon grades solidification is complete at relatively low temperature, maybe 1300, maybe 1250, may even come down to 1200. But even after solidification is over, the shells, the solid, that means the whole solidification is completed, you have only solid shell. The solid shell is now coming down the caster, the temperature is also coming down, but there are certain temperature zones, I will come to it later, which is relatively brittle. That means it cannot withstand stresses or strains in those temperature regions. So that is why we have to be careful not only during solidification, but even at temperature lower than solidification. That is why I have mentioned this temperature range of 1400 to 600 centigrade. In this temperature range we have to be careful, we should know what is the strength and toughness of the solid shell, whether it can withstand the stress or strain which is continuously forming during solidification and even subsequent to solidification during secondary cooling. So we have to be careful about that. So these issues are important for controlling formation of crack in solid shell. If we can control formation of crack, we will have a relatively good quality of solid shell, the cast product will be relatively good, we need not worry about it during subsequent processing of it.